Today we're going to think a little bit about relationships between categorical variables. You may recall that a categorical variable is a set of data where the individuals can be put into different categories, such as male or female or working or not working, etc. And we're particularly interested in when we've got one category and another one where we think there might be some kind of connection between the two that gives us some insight into what makes the world work in some form or other. The example that we looked at in the previous video was where we were looking at different types of chronic diseases, and in this particular case we had asthma and cancer and so on, and we were trying to make some kind of connection between those and the amount of exercise that people have, whether they are in the high exercise category or moderate or high, or in the low exercise category. So there's two dimensions to this particular person. We've got two characteristics that we observe about each person, and on the basis of that we can construct this table. This table looks a bit different to the one you saw previously. Before we had just the number of people in each category and some percentages, but now we've turned these into probabilities, to fractions of 100 or fractions of 1. And that's because we want to convey the idea that these numbers here are actually probabilities. So, for example, if I think about the numbers here, that there is a probability that a particular individual has asthma and they engage in minimal exercise. So if I took 1,000 people, or 100 people rather, to keep it simpler, and I knew something about their exercise status and about their chronic illness, then 5.2 out of those 100 people would have asthma and would engage in minimal exercise. 2.5 of those people would have cancer and engage in a moderate or more exercise. So these are probabilities of this being true and this being true. So it's what's referred to as a joint or a total probability. Joint or a intersection probability. In contrast, I'll finish telling you about it here, and then we'll have a look at some of the description on the next page. These numbers here in the end columns are essentially just the probability of a person having asthma. So 8% of the population have asthma. 64% have none of the above illnesses, etc. So they're what's referred to as marginal probabilities, because they're just the probability of one particular characteristic taking a particular value, ignoring the other one. So we don't know whether these 8% here, how many of those people get a lot of exercise and how many get not much at all. We're just looking at the characteristics of whether they have asthma or not. Okay, so that's kind of the two different types of probabilities we've got here. So the values in the margin are referred to as marginal probabilities. In the example I gave you, I concentrated just on the probability of a particular type of illness, but I could also have just looked at the particular exercise category, so people who are engaging in moderate exercise, there's a 0.3568 chance that person is in that category. And probability of diabetes, 0.0404, that's that number there. Okay, so that's kind of the marginal probabilities. The other type of probabilities are joint or intersection probabilities, which are the ones that I highlighted at first, which is when you've got a particular row and a particular column, you look at the intersection between those two, you get a probability of a person having diabetes and minimal exercise, 0.09292. Let's go back to the thing and you'll see that. Diabetes, minimal exercise, so that gives us, there's the diabetes case, there's the minimal exercise case. Intersection of those two is 0.0292. So that is indeed an intersection probability. The person has to have both this and this. And if they have that, there's a 2.92% chance that they'll be in that category. Okay, so that's a joint or an intersection probability. So when you look at a table like this, it comes out of a set of data. What we're trying to do here is communicate some of the basic ideas of probability that go along with that. And the most foundational building blocks of probability when you've got two characteristics of interest is you might be interested in one of those alone, in which case you're looking at marginal probabilities, or you might be looking at a combination of them, in which case you're most likely looking at joint or intersection probabilities. This also reminds us what a probability actually is. A probability is just like what you might describe as a relative frequency. So these numbers in the table here, we had 5,000 people. and we had a certain number of people in each of these categories, and we just took the proportion of people in that category, and that becomes a probability. So when you think about a probability, that's what it is. So talk about the probability that it's going to rain next week. Well, that will basically be the number of times it rains in a given week divided by the total number of weeks. So if it rains 30% of the time, then the probability it will rain next week is 0.3. So that's what all the probability is, and this is precisely what we're describing here with the way we've constructed those probabilities. Now, there was another thing that we did with our table, which we produced in Excel using what's called the pivot table option, and you'll learn about that in your workshops and tutorials, is that we took those probabilities here, and instead of just looking at them in their raw form, we can actually divide by the total of each column, for example, and get the percentage of column, or by the total of each row and get the percentage of row. So let's take the numbers in the first column and divide them all by 0.6432. And then let's take all the numbers in the second column and divide them by 0.3568. When we do that, we end up with a table that looks like this. So that number there, 0.0808, comes from, if I can, 0.0520 divided by 0.6432. So, and that will give you 0.0808. So these numbers are also probabilities, but they're just a little bit different. These are no longer the joint or intersection probabilities between these two characteristics. In fact, what we're now measuring is what's called the conditional probability. You're saying, let's just consider the people who engage in minimal exercise, this group of people here. Just thinking about those people, what is the probability that a person who engages in minimal exercise has asthma? Answer, 0.08. What's the probability that they have heart disease? 0.0684. So only considering this subset, what's that probability? So that's kind of like, given that the person engages in minimal exercise, what's the probability of this particular illness being their primary illness? So that's what we refer to as a conditional probability, which is what we describe on the next page here. So these probabilities are conditional probabilities. The probability of having diabetes, given that you engage in minimal exercise, is 0.0454. We use that symbol there, the vertical line, to indicate conditional, or given that you engage in minimal exercise, what's the probability that you have diabetes? And you see that 0.0454 right here. Okay, so that's your third type of probability that you can make sense of by looking at these tables. Marginal probability, probability of one particular value occurring, in one of the dimensions, one of the characteristics, joint intersection of two things. Conditional, given that one of the characteristics has a particular value, like minimal exercise, what's the probability of having this particular type of illness? Okay, so that's our different sorts of probabilities that we've encountered. Now we can make use of these different things to answer quite an important question. You may recall at the end of the previous video we started to speculate that it looked like there was some kind of connection between exercise and illness, that certain types of illnesses are more common amongst those who engage in minimal exercise, or as opposed to moderate exercise. So, and that's not surprising. Common sense would tell you that if people are fitter and healthier and exercise more, then they're less likely to have certain types of illness. It's less likely to have heart disease or diabetes or something like that. So that's sort of common knowledge. But it's handy if you've got some techniques in your little data analytics toolkit to be able to sort of explore whether that's actually true in the data that you've actually got. So we're going to just introduce a really simple concept of what's called statistical independence as a way of exploring that. And we're doing it in a sort of mechanical way at the moment, and there'll be some complexity we've got to add to that a bit later on. But for now, it's just to give us a taste as to whether in this table of numbers, which kind of looks, maybe there's some interesting things here, it's a little bit unclear how we kind of deduce that. We actually have a technique for answering that question as to whether there's any relationship at all between exercise status and the kind of illness that you're likely to be suffering from. So the way it works is the following. Let's just take diabetes, for example. We'll look at the three tables that we've got in the previous things. Let's concentrate on diabetes, and we're going to flick our way back over those three tables. The probability of having diabetes overall is 0.0404. Okay, so 4.04% of the population have diabetes. These are the conditional probabilities, conditional on your level of exercise. So we can actually get all the numbers we need from here. So a person, if we just randomly picked a person out of the population, they've got a 4% chance of having diabetes. Now these are conditional probabilities. So now if you just go to the people in the population who engage in minimal exercise, so just consider the subset of the population who engage in minimal exercise, the chance that one of those people has, has diabetes is 4.54%, so a little bit higher. So there's something different about these people compared to the others. So there's a 4.04% chance of just a randomly chosen person in the population having diabetes. But for those who engage in minimal exercise, there's a 4.54% chance that one of those people will have diabetes. For those in the population who exercise quite frequently, moderate or higher, then there's only a 3% chance that those people will have diabetes. So there's something different about these people compared to these people. The people who engage in moderate exercise have a much smaller chance of having diabetes than those who engage in minimal exercise. That's a clue to us that there's a relationship between the amount of exercise you have and your likelihood of diabetes. So we see that kind of conversation written out here. The probability of a person having diabetes is 4%, 4.04%. The probability of having diabetes, given that you do minimal exercise, is actually bigger. So if you do minimal exercise, you are more likely to have diabetes. If you do moderate or frequent exercise, you're actually less likely to have diabetes. So that suggests to us that there is quite a clear link between having diabetes and the amount of exercise you do. So there is a dependency between these two variables, okay, and that is what we're talking about with independence. So the technique that we've used here to answer that, so that's the intuition behind why we think that incidence of diabetes is related to exercise, that the fact that these three numbers are different tells us that there's a connection. So writing that down in the form of an equation, what we've said is the probability of having diabetes that you get minimal exercise is different to the probability of having diabetes if you have moderate or more exercise. And it's different again to the overall probability of having diabetes. So because those things are not equal to each other, we would say that the exercise status and the incidence of diabetes are not independent. For them to be independent, we would need all of these three probabilities to be equal to each other, and that's what this statement here says. So if those three were equal to each other, we would be claiming that your diabetes status was independent of how much exercise you get. So an independent example might be, the colour of your eyes, for example. People with brown eyes more likely have diabetes than people with green eyes. Well, you'd have to say probably not. There's absolutely no reason for there to be any connection between those two. So if I just looked at the incidence of diabetes, and then I looked at the incidence of diabetes amongst people with brown eyes, and the incidence amongst people with blue eyes, I should get pretty much the same probability in every case, because really there's no connection between the colour of your eyes and whether you have diabetes, unless there's some weird thing that I don't know about in terms of how the colour of eyes relates to your body or something like that. In this case, we've got something where, not surprisingly, we do start to see a connection between the two of them, and that's essentially what independence is telling us about here. Okay, so we've defined independence here by saying that the probability A and B are independent if the probability of A given B taking a particular value is the same as the overall probability of A. So the probability of diabetes given minimal exercise is just the same as the probability of diabetes overall. That's the intuitive way of thinking about independence, and it kind of makes sense intuitively. If it doesn't depend upon the value of B, then they're independent of each other. If it doesn't depend upon the colour of your eyes, then the probability doesn't depend on the colour of your eyes, then they're independent. Now look, that particular approach to independence is by far the easiest way to understand intuitively, but you can actually play around with formulas here and rearrange that and write the same kind of statement in a slightly different way, and that's what this second formula here is doing. We could also claim independence by looking at the marginal probabilities and multiplying them together and seeing whether they equal the joint probability or the intersection probability. So in this example, if we go back a few slides to the complete table before we actually started taking conditional probabilities. Here it is here. You see the probability of having diabetes is 0.0404. The probability of engaging in minimal exercise is 0.64. And the probability of diabetes and minimal exercise is 0.0292. Just remember those numbers and come forward a few slides to where we're back now. 0.0292 is the probability of both. Probability of this marginal minimal exercise is that, and probability of diabetes is that. Multiply those two together. Do they equal 0.0292? Answer, no they don't. So that 0.0292 is different to the 0.0262, so they're not independent. So that's actually the same check as what we did previously, but actually, look, to be honest, it's not as good a check because the intuition is not there. Why does this multiplying kind of tell you anything about independence? And the answer is it's got to do with the interaction or the formulas that are used to relate joint, marginal and conditional probabilities together. But the one that's much easier to follow is the one on the previous page where we just look at the relationship between the conditional probabilities when b equals this value or that value or the overall marginal probability. Okay, so that's the idea of independence. Most times your intuition would tell you whether you think something, two characteristics are independent. You know, you'd like to believe that exercise has some effect on your health, and so not surprisingly your data confirms that indeed that's the case. You'd like to think that the colour of your eyes has no effect on your health, and so if you had data on that, you'd be able to check and find out that perhaps there's really no difference in the probability of having a particular illness regardless of your colour of your eyes. What we've got is now a method statistically to actually check out whether your intuition actually is right. One small problem with this method is that so far we're just saying, look, if these things are not equal, then they're not independent. But what about if they were kind of close to each other? You know, 0.026 and 0.0292 aren't that different. So they might not be exactly equal, but if they were kind of close, then maybe that would say, look, they're virtually independent. There's a little bit of sort of randomness sometimes that comes into a set of numbers. So in fact, we need something a bit more sophisticated than what we've done here. And we'll get to that later on in the course when we introduce the idea of random sampling and testing for differences, because sometimes differences like this are just little anomaly quirks of the data, and they're not real differences. So we need to have a more sophisticated approach to that, and that's what we'll actually address later in this particular set of videos when you get to that point. Okay, I hope you found that interesting, and we'll look forward to seeing you again.